In this video, we will be discussing a specific type of a joint named Hooke's joint, also sometimes called as a universal Hooke's joint. It is a joint which is connecting two shafts. These two shafts will not be in a same straight line with each other, because if the two shafts are in a same straight line along like these, then what we could do is we could add only a simple straight coupling. In that case, rotation of the input shaft would be exactly equal to the rotation of the output shaft. If the two shafts are in a straight line and if you have a simple coupling in the middle, then velocity of the first shaft and velocity of the second shaft would also be the same. So they would go together. Today we want to discuss a case where if the angle of the input shaft and the angle of the output shaft is not collinear, or if you visualize this pink colored pen is the output shaft, and what if they are aligned at an angle like this? In that case, this is the angle between the two shafts. Then a joint which is used to couple these two shafts which are at an angle is called as an Hooke's joint. A very easy schematic diagram is shown here in the figure 1. Input shaft, if you notice, has a C-shaped clamp along the x-axis, is shown very clearly. Connected to that, exactly in the same geometry, is the output shaft, which was my pink colored pen, having a similar C-shaped clamp, but the difference between the two is the C-shaped clamp of the input shaft if it is my left hand, and the C-shaped clamp of the output shaft if it is my right hand. Then the output shaft while assembling is rotated by 90 degrees, and then these two are clamped to each other. So this is exactly how the two arrangement looks like. Now definitely I would need a third link to connect the input and to connect the output shaft. By geometry, the C-shaped link and the shaft input and the C-shaped link and the output shaft, the geometry wise they are exactly the same. Now to connect these two, what we use is something called as a cross. It is actually named as a cross. So it is very clear from this diagram, this spherical shaped diagram and with a cross is actually the third link which connects. Now there is complete rotational motion involved, which means input shaft can actually rotate about this x-axis, clockwise or anti-clockwise. The output shaft along with its C-shaped clamp can rotate about this vertical axis, and it is the cross in between. Now in this diagram you can see a sphere and the two arms of the cross coming out. In real life it is actually a square shaped element which is placed in the middle. Now in this video we are interested in actually deriving and understanding the position equation. So let's get into the motion of this thing. If the input shaft rotates by an angle theta, corresponding output shaft will not rotate about an angle theta. This output shaft, let's say, rotates about an angle phi. Now why these two angles are not the same is because there is an angle alpha, which is the change in the angle inclination between the two shafts. For a particular Hooke's joint, the angle alpha is constant. Now initially in this video we would be interested in deriving the equations between the position equation theta and the corresponding position equation phi. To understand that, let's imagine the basic concept of engineering drawing. If you look at the whole Hooke's joint from the input shaft axis, A and B would appear to be horizontal diameter. Input shaft would be something like this pen which I am holding coming out of the plane of the board, and output shaft would be behind. Now very clearly, if we imagine the rotation of the input shaft as marked by this arrow, and if your viewing angle is from the input axis, A would happen to travel along the arc of a circle and B would happen to travel along the arc of a circle. Now because of the shaft angle alpha, when AB rotates at an angle theta as marked here in this diagram, basic engineering drawing principles will tell you that these 2 points C and the lower one D, which is there in the bottom down there, would definitely travel along the path which is traced by an ellipse. So path of AB is a circle as seen from the shaft axis 1. At that time, CD would trace a path which is an ellipse. We are now interested in therefore finding if input shaft rotates by an angle theta, what is going to be the corresponding rotation of the output shaft. Now, to get a very clear picture from this, what we should understand is AB represents the input shaft, whereas C, O and D represents the output shaft. When AB rotates by an angle theta, path traveled by A will go to A1, B will reach a point B1. Therefore, the new position of AB would be A1, B1. Angle rotated would be theta. In the same time, C would actually come and travel along and occupy a position C1. Now, if you mark and join the two lines between O and C1 and you measure the geometry, you would actually get the same angle as that of theta. So very simple basic concept from engineering drawing would make you recollect that this angle theta is not the true angle of the output shaft CD, it is the apparent angle. Whereas the true angle is obtained by using very simple concept of engineering drawing. So from the front view, we will project our views in the upper plane, which is the top view. We will make the top view parallel to the x-axis and project it back down in the front view, and hence OC1 dash would be our angle of true inclination for the output shaft CD. In the next video, we would see how to get a relation between theta and phi.